So I will be talking about non-commutative resolutions of discriminants, but before that, I first want to thank the organizers for giving me the opportunity to give a 50-minute talk here. And I should also mention that this here is joint work with Eleonore Faber, is here, and Colleen Ingalls is not here. And this has been going on for some time. And so, what is this all about? So, it says in the title, I will explain everything in the title. So, non-commutative resolutions, we heard something about that from Examo on Monday. And discriminants means discriminants of reflection groups. And the initial goal of this work was to find non-commutative resolutions of singularities. So NCR is always non-commutative resolution of some non-normal hyposurfaces. And somehow we ended up considering these discriminants, and this leads to some kind of McKay correspondence for reflection groups. Okay, and so what will I do in this talk? So I will explain what are these discriminants of reflection groups and what is this non-commutative resolution we can construct, and hopefully how this corresponds to the McKay correspondence. And in the end, if I have time, I also have some pictures of this, because all of this is very geometric. And so we'll start with part one. So this is reflection groups and discriminants, which are usually denoted by delta. And so for this talk, I will assume that we are over a nice field of characteristic 0 and C. So not to have any, so probably most of the results will also hold in characteristic C if the order of the group the characteristic does not divide the order of the group, but keep it simple, K is equal to C. And also we will consider finite subgroups G in some GLN K, and they will be generated by order 2 reflections. So in some sense, like 2 reflection groups. And so an example already appeared in Hugh's talk. He was at Hawaii group, so you can think about these groups. And so, okay, so we start with a group, then G X, a vector space V, so an n-dimensional K vector space, and also S, which is symmetric K algebra of V, and so this is just the polynomial ring in n variables. And okay, so group acts on the polynomials, and so it's just like we let the group act on the coordinates and then on the polynomial. And so we can also consider the invariant ring T. These are all polynomials which stay invariant under G. And you might recall a very classical theorem from Chevalier-Shepherd-Todd, which says something about these invariant rings. So Chevalier Shepherd and Todd tells us what is the structure of these invariants, rings. So if I take now not a reflection group but any finite subgroup of GL and K, then we have the following P. So this is the invariant ring is a polynomial ring, or multiple polynomial ring and only if G is generated by pseudo-reflections. Okay, so I won't really explain what pseudo-reflections are. Basically, groups containing reflections of higher order too. And so this tells us basically this invariant ring is nice and smooth and doesn't have any singularities if and only if the group is a reflection group. And if it's not a reflection group, then so the invariant ring does have singularities, but well, we probably will see something about that. And so now we can consider T. So this is isomorphic to a polynomial ring. So we have one out here at N, and this is contained in S ring where it acts on. So this Fi, which are the so-called basic invariants, and there are polynomials in the X line. And geometrically, we get projection from Pi, so I write here spec of S, so this is just isomorphic V, onto the quotient spec of T, which is the same thing as V mod G, and so this is a map between two smooth spaces. But there are singularities, so if there weren't any singularities, we wouldn't need to have to consider any resolutions of singularities. So where are the singularities? So in S, we can consider, so we can look what does the group do, and there is the so-called reflecting, the hyperplane, so the set of mirrors of the reflection group. And so in here is the mirrors of the reflection group. So they are given by one polynomial, so it's just the product of some linear forms. So this polynomial is usually denoted by set, and so this is the product of, I'll just write LG, G, to assume group is generated by reflections. And this is the hyperplane arrangement, and then we can look what happens if we project it onto the quotient, and that's where the discriminant appears. So the image of the V of Z, so image of the hyperplane arrangement is our delta. This is the discriminant. And this is usually very singular. And I mean, algebraically, you can actually write down these theoretically very easily. So Z is given by the Jacobian of these F1 to Fn with respect to the axis. And so this is just the Jacobian, is the determinant of the Fi J. So this lives apparently in here. And the delta is then given very easily as Z squared in case we have order 2 reflections. And 2, so just an example. So what are the objects we're actually looking at? So one of the, the easiest example probably would be if I just consider D equal to mu2, but then there is not much geometry in there. So I'll take G equal to mu2 cross mu2, and they could act in the polynomial ring of 2 variables. And so this here is these 2 generators, 1 and 1, 0, 0, minus 1. And so then I can write down very easily what is T in this case. So T is always the invariant ring. That is kx squared I squared. You can see that it's still a nice polynomial ring. So this would be the F1, this would be the F2. And then Z is given as the Jacobian of these ideals. So just get this is 4 times x times y, so a normal crossing divisor, and z squared. The discriminant in this case is just I squared this, so I get x squared, y squared, if I just forget this constant factor here, and this is f1 times f2 in the quotient. And so here the picture is not very interesting. What do I see here? So this axiom from C2, and the hyperplane arrangement is given by x times y equals 0, so this is the set, and the projection onto the quotient doesn't give me anything new really. This is just f1 times f2. So it looks exactly the same. But you can still generalize this to same for mu 2 to the power n acting on the polynomial ring in n variables. And then you get that delta is a normal crossing divisor. So this means it's just like a union of hyperplanes, so it's as nice as you might think, but it's still very singular. And the second example was where it's a little bit more exciting. If I take g equal to s3, then, well, I don't write down all these notions because it gets messy with the f1 and f2 already. So the picture here is I have 3 mirrors, something like this, and the discriminant here is something well known. It is the test. And as you see here, this is also a singular curve. And so in general, one can show that these discriminants, so these deltas, are singular in codimension 1. And they're even called, we have a structure which is called cycle divisors. So, meaning singular in codimension 1 means it's not even normal. So the singularities are, in some sense, really large. And you might think this is like the opposite of the thing we're usually considering. So usually we're happy if we have something with isolated singularities. We can do some out-on-the-right sequences for that. But in general, if you have something non-isolated, it's very hard to say something about, well, representation theory and maximal Macaulay modules. So especially, it's not quite clear what these non-commutative resolutions should be. So first of all, it was like, can we even find non-commutative resolutions? So the question, how can we construct non-commutative resolutions for these discriminants? And okay, before I come to the non-commutative, to constructing them, I should actually recall what Osamu told us more or less on Monday, but if you hear it twice, maybe it's easier to remember or to grasp what it actually is. So let's do that. So what are non-commutative resolutions and non-commutative Krapin resolutions? So, well, they're coming, so the idea is we want to resolve singularities. If we do that geometrically, then you get something very complicated because you're blowing up things and you get complicated rings. So the idea was to find some algebraic object which is in some sense closer to the original ring. And so this is coming from the rational geometry, from the Born-Orloff conjecture. And so historically, first there were these non-commutative Krapin resolutions introduced by Vandenberg, and then later on there was this NCRs more generally introduced by Dao, Yama, Takahashi, and Via. But let's give the definition. So we have like R, the commutative Noetherian ring, and we'll tacitly assume here that R is reduced, so you can do the definition without that assumption, but then it gets more complicated. And then an R algebra A is called NCR, so non-commutative resolution, if, well, you have seen it is of the form, it is an endomorphism ring of some module over R, and this module here is sufficiently nice in the sense it's finitely generated and faithful, so supported everywhere. And okay, these are the conditions, but what is the main thing is, we want to have that the global dimension of this thing, this A, is finite. And so this means if this A was commutative, then global dimension finite means the ring is actually a regular ring. So this should somehow mimic this non-singularity condition. And so this is the definition of Dao Yama Takahashi and Real. And then the stronger condition, which was historically earlier, is from Vandenberg. So although finite global dimension is a nice condition, so this A can be non-commutative and can be still terribly complicated. So A is a non-commutative Krapent resolution. So the Krapent also comes from irrational geometry. If A is a non-singular order, so what does that mean? So this means that the global dimension of A localized in any prime P is equal to the full dimension of R localized in P for all P spec R. Okay, so this, I mean, I won't dwell into what does this actually mean. But so the idea is that this Krapent resolution somehow gives you is some sense of oops, and I forgot the second condition. Plus A is maximal co-matrix. So this belongs it here. So this means that this ring A is homologically homogeneous, meaning that all the simples have the same projective dimension. So it's as nice as it can be, whereas this one here is, well, we don't say anything about the projective dimensions of the simples, just that they are finite. Okay. So this looks all very complicated, so I'll give you an example so you can think about something. So there is one classical example, like the example. This is the classical McKay correspondence, which also is some link to representation theory, because so far we have only done more or less geometry in algebra. So what is the McKay correspondence? So again, we assume now, so keep the reflection groups in mind. The reflection groups are always called G, but now we are considering groups gamma in SL2K. K is again our nice field C, finite, and this acts again on the two-dimensional vector space, V, and again we have we denote by S this in V. So same situation as before, but now SL2K, and we denote R the invariant ring of S under gamma. So nothing happens, but we've seen Chevrolet-Shepard-Todd tells us this invariant ring is regular if and only if there's a reflection group, so this is not a reflection group. So then, spectrum of R, so this is just the variety, so this is the quotient singularity d mod gamma, so this is a quotient singularity, and this is a so-called Kleinian singularity. So what does that mean? So Klein means that these singularities are sufficiently nice, so there are still hypersurfaces or surfaces in C3, and they only have isolated singularities. And they are classified by ADE Lincoln diagrams. And that is a little bit complicated how to do that. So how can you classify them with Lincoln diagrams? So you have your isolated quotient singularity. Then you consider the minimal resolution of singularities. On this minimal resolution of singularities, you have so-called exceptional curves. And then you consider how these exceptional curves intersect, and you get this resolution diagram. And so, just to give one example without actually explaining everything, if I take the nice D4 singularity, so D4 is given by C squared, so we are in the, so S in this is in this case, so it's okay, so it's, I said it's been, forget about that. So it is a hypersurface in C3, so we can, it's given by one polynomial, and this is given by z squared plus x times x squared plus y squared. And the geometric picture is this, so it looks, real picture of the singularity is like this. And I have another color, there was some red somewhere. So we have one isolated singularity here. And then resolving means first we do one blow up and we change singularities here. So we pull them apart, and from this blow up we get one exceptional curve, which is somewhere here. And then we do another blow up to finally separate all the singularities, and we end up something which looks schematically like this. So here is the old exceptional divisor, then we get three new ones which intersect like this. And so this Lincoln diagram, so you should get, since I called it D4, you should get a D4, and maybe you see it. So this is the first exceptional divisor to D3, D4. So for each exceptional divisor, we do a dot, and we connect them, the two of them intersect. So this, we have the E1, E2, E3, E4. So that is the resolution diagram. And so this is purely singularity theory still. So now enters the representation theory with McKay's observation from 1979. So he was a group theorist, so he played around with group representations, and somehow he considered, like if you tensor representations, he considered graphs arising from this tensoring, and so considered so-called McKay graphs, which you get where the vertices are now the irreducible representations of the groups, and you connect them if one of them is contained in the tensor product with the canonical representation. But this gives, so we did that for all these finite subgroups here, and what you get is a one-to-one correspondence between first three things, well, two things in the beginning, namely the irreducible representations of gamma, modulo the trivial representation, so this is somehow too much there, and on the other side, these exceptional curves there, so the incomposable components of the exceptional divisor on the minimal resolution of X. And so this gives like a very nice link between representation theory here and, representation theory is here, and geometry here. And then later on, my organization of the board is really bad. Well, put that here. Later on, this was, well, of course, this was explained why this is the case, but there is also an algebraic version of this. So you can not only get to the irreducible representations of gamma, but also one-to-one to the indecomposable maximum Cohen-Macaulay modules over the invariant ring R as gamma. And this here is Alexander. And then we'll talk a little bit more about this version of the McKay correspondence. So McKay correspondence ring, we have this one-to-one correspondences, and we're in particular interested in this side. So indecomposable maximal Cohen-Macaulay modules over the invariant ring correspond one-to-one to irreducible representations of gamma. And okay, so far so good. So let's look at this a little bit better, because this will then also give us somehow the idea how to connect all of this with reflection groups into discriminants. So what does Alzheimer's here? So this is from 1986, and so it's precisely, it's a little bit more general. So this here, so the classical McKay correspondence is if gamma is a finite subgroup of SL2K, but what Auslander says is basically all dimensions. So if we take gamma in GLNK, small, so small means no pseudo-reflection, so in particular it's not a reflection group. Pseudo-reflection. Then we can look at the following thing. So we look at the so-called Q group ring. So this is S star G. Q group ring. And so this is just, you can think of this like the elements are sums of SG. G is in, well, and now G is gamma. Sorry for that. Gamma, and here are probably going from gammas too. Sorry about that. So the elements in this ring are the sums of polynomials and group elements, but the multiplication is a little bit twisted. So this is why this is also sometimes called the twisted group ring. The multiplication is, if I take an S gamma and multiply it with S prime gamma prime, then I end up with S gamma acting on S prime, and the group just have the normal multiplication. Okay, so consider this ring, and what does the theorem say? It says that we have a map from A, so S star gamma, to the endomorphism ring over the invariant ring, so S gamma of X. this here is R. So you see, so R is always in the under gamma. So this is isomorphism. So somehow we have an endomorphism ring showing up there, and it's even better, namely that this S star gamma is maximal Cohen-Macaulay over R, and also global dimension is n, and it's even over the right center, so the center of S star gamma is R, invariant. So it's as perfect as it can be, because if you look at this definition, so we have an endomorphism ring of a finitely generated module over R. It is a finite global dimension, and it's even Cohen-Macaulay, so it's actually a non-commutative Kraft resolution. This is the corollary of the mark that A, this Q group ring, gives us a non-commutative Kraft resolution of R. Okay, this is nice. So if we were considering these invariant rings of small subgroups, we would have found now very nice non-commutative resolution. And so in view of the McKay correspondence down here, we also get, maybe I'll write that up here, we get also a one-to-one correspondence here between the projective, so indecomposable projective S star gamma modules, and this is also one-to-one to the R summons of S. So S is an R module. If we decompose it as a direct sum of R modules, then these direct summons correspond to the projective modules here, and they correspond, well, this is only in dimension 2, to all the indecomposable maximal Cohen-Macaulay modules. Okay, and yeah, of course, they still correspond to the representations of the group. And a remark here is that this algebra can also be seen as, so this algebra, so it's S star gamma, is Morita equivalent to the pre-projective algebra of the, so delta tilde here, which is unfortunate, this is the extended Inkin diagram. So this is work by Reiter and Vandenberg. So it has a nice algebra structure, and we know if we have a pre-projective algebra, we know what are the relations, so we just have the pre-projective relations there. And I don't want to say more about the McKay correspondence, but there have been various generalizations in higher dimensions and other singularities, but so far not to reflection groups. And so now we basically, so in the first part, we had reflection groups, and we had these horrible discriminants with the horrible singularities. And in the second part, we saw if we don't have a reflection group, so if we have a small subgroup, then we can find this very nice non-commutative Kraft resolution. So the idea is, of course, well, why don't we combine all of this and get a non-commutative resolution of the discriminant? So this is now part 3, so the NCR of the discriminant delta. Okay, so we want to do that, so we cannot just take this S, I mean, if we have G, and G, L, and K, reflection group. So what's the first problem is, well, we can still consider this Q group ring here. So we still have that. And it's still of global dimension n. It's still nice. So we still have the S star G. But the problem is it's not isomorphic to the endomorphism. So, but this is not isomorphic to end TS. So remember, T was always the invariant ring. So this is S and the reflection group. So somehow this Auslander result cannot really hold, but it kind of does. Because we can somehow, so it's not an endomorphism ring of S over this invariant ring here, but if we play a little bit around with the rings, then we can prove the following thing. So this is our first theorem. And so if G in G K is a true reflection group, then we can consider the gamma here, maybe we just take G and intersect with the SLNK. So this will give us a group which doesn't contain any pseudo-reflections. Then we denote R the invariant ring of gamma by T the invariant ring under G. And then we have, well this is, so gamma is a subgroup of G of index 2, so we have an exact sequence of groups, which is either split. One goes to gamma to G, goes on to the quotient, goes to 1. And so this quotient here is, since it's of index 2, this is just isomorphic to mu2. And so we can think of this as generated by one element here. We'll be interested later. So we have this exact sequence of groups. And then our Q group ring S star G is isomorphic as a ring of the endomorphism ring of R star H, and here I take S star H. So what does this mean? So I have to twist with the quotient here. And so, well, we still have, I mean, I won't say anything about the proof, it's a long calculation, but the problem is now, so we see that A is still an endomorphism ring, but somehow over the wrong ring. So I have here the R is the invariant ring of the small group, and H is just the quotient. And so we can, which is nice, we can recover Auslander's original result by just setting this, if the H is trivial, then just the same thing as here. But, yeah, and maybe I should say that also the center is not that what we want, but it's good. So the center of this thing here is T. Okay, so we somehow, we're getting closer, but we are not where we want to be. So we want to have a non-commutative resolution of this discriminant. So far we have kind of a resolution over a weird ring. And but what can we do now? So if we look at this endomorphism ring here, then we can kill some things. And so we denote by E plus minus the two idempotents in here. So this is 1 plus minus sigma in R star H. And, okay, so any idea what we could kill here? As I'm erasing the board. So we have two idempotents, and let's see what happens. Maybe I'll leave that. What happens if we kill one of idempotent. And with killing, I mean, we just consider the usual recoulement. So we take the recoulement for, B is R star H, and we get rid of, let's get rid of B minus. Then we have, I'll just draw the leftmost portion of this recoulement. So here we have the I upper star, which is in this case just canceling over B with B mod B, B minus B, and then get here mod B, B minus B. Okay, so we have some match between these two module categories. But what is a good thing about this map? So if we look at this quotient here, and we can calculate, well, this is nothing else than T of delta. So T is the invariant ring of the reflection group. Delta is exactly what we want. So this is a discriminant. So this is good. So we go from these modules, the modules over this Q group ring, to the modules of T mod delta. But of course the problem is that this recoulement is not really an equivalence of categories. So we have, this doesn't work. So we have to work a little bit more here. There's but the next theorem is the following. We can show this is not, well, this is an equivalence, but we have an equivalence on the level of maximal Cohen-Macaulay modules. Namely, if we mod out by the ideal B minus B, and this is equivalent to the maximal Cohen-Macaulay modules over the discriminant. And so this is actually, well, this is following work of Nora, who did that in dimension 2, and we now extended that to dimension n. And so now the rest is more or less easy. Namely, we can compute this I upper star of A, and we find that this is an isomorphism ring over the discriminant mod delta I upper star of S star H, whatever this module is. And so this, if we just compute this, and on this side, if we just look at this quotient here, then, okay, well, it's still readable, then in here we get, well, we have to mod out by this ideal, which means we have to see, well, which morphism strikes here to this E minus B, and what we get that A in here goes to A bar, which is isomorphic to A mod A E A, and E is the trivial idempotent. So this is just 1 over the order of the group, and then I just take the sum of the G's. Okay, and so, okay, so we have 4 minutes left, I guess. So we just state the theorem, and then I have some pictures, and also, so this is now main theorem. Namely, we take G and gamma as before, and then A bar is isomorphic to this isomorphism ring, T mod delta, I upper star S star H. So this is a NCR of T mod delta, so it's not crebant because we're somehow of global dimension n, because somehow this T mod delta is only the hypersurface in T, so it's of crude dimension n minus 1, but this thing here still has global dimension n. And so this is one thing. And then you might wonder, what is this thing here? So can we say something which module this is? So we know it's a maximal Cohen-Macaulay module. But this has also a very nice geometric interpretation. You can show that this is isomorphic to S modulo Z. So Z was the hyperplane arrangement. So what we get is that the discriminant is in some sense resolved by this hyperplane arrangement, which is up in the original vector space. And so let me just say something. So here this global dimension n. This also follows from Auslander, Weizsäcker, Todorov. And getting this isomorphism, this is the work of standing. Okay, so now we have our non-commutative resolution, and maybe I can probably already put on the screen. So, but for the McKay correspondence, we get again something, namely we get that the indecomposable projective A-bar modules are in one-to-one correspondence with the additive summons of T mod delta of S mod Z, and we get here one-to-one correspondence between the non-trivial G-rings. So we have our correspondence here, and so how many minutes do I have left? Like 3 minutes. Okay, perfect. So okay, oh, that's done. So here I just wanted to state the result again for dimension n. So for dimension 2. So let us look what does our result say, or like how does it look like in dimension 2. So this is the classical theorem of Felix-Klein. So if we have this finite this quotient by SL2 finite subgroups, then we get this list of ANs, DNs, D6, D7, and D8. So these are the hypersurfaces. And then if we take the reflection groups, so basically what we have, I had a pointer somewhere. So we have the reflection group, and the Kleinian group is just G intersected with SL2C. And so the corresponding discriminants of this are, well, we just take the equations from before, and the Z squared gets killed. So these are the discriminant curves of this reflection groups in GL2C. And so here are some pictures of this. So these are the first two, A1 and A2. And so in A1, so the discriminants are always in blue. So you see that this here, the Kleinian singularity is the cone. And here is the singularity, and here the discriminant curve, you cannot really see very well, is the normal crossing divisor we had before. And here in A2 you get the cusp, so this is the discriminant of S3. And then we have the higher ANs, which, well, they just get like more singular. Then here is the D4, which I tried to draw. And here you see that the discriminant are just the 3 lines. And the other DNs also look similar. And you see also here that the discriminant is not necessarily irreducible, but can have more components like here. And then we have E6. Oh, now it's better. E7. So E7 already looks quite complicated. And the last one, E8, doesn't look complicated at all. So, but it is E8. And so the discriminant curve is here. And so the last thing I want to, so this is the result in dimension 2. And so in dimension 2, I didn't say much about this representation generator, but we actually get that S mod Z is a maximal Cohen-Macaulay representation generator, because we get all maximal Cohen-Macaulay modules. And just one example in higher dimension, which is the discriminant of S4. So you see here, this is already quite complicated. Still a hypersurface, always. And it has two singular curves here. And what is now the non-commutative resolution? And so how can we see that in terms of this G? So here is the McKay graph. So it's indexed by the Young tableau, you've seen in talk before. And S mod Z can be decomposed as the sum of four modules. And then we get a geometric interpretation of these four modules, namely, first of all, we get the ring itself, we get the Jacobian ideal, which is all of the singularities, then we get the syzygy module, which is something with higher rank, and this here is just one component of the singular locus. And so the last slide, I'm sorry for being a little bit too long, is so we computed all of them, but in general, can we say what are these R-direct summands of S modulo Z? So do we always have a nice geometric interpretations of these? First question. Then second one, we can draw the McKay graph, which is already not so easy, but it's doable, but we have no idea so far what the relations are. So does this have something to do with the pre-projective relations? And what about the geometry? So can we somehow see that as resolution? Okay, that's all.